Hello and welcome to Project 152, your weekly specialist exam prep. Every week we cover some questions that the QCAA have done. If you stick with it the whole time, you'll have done every single question they've ever released. We are up to week 10. It is a tech active week, so make sure you've got your calculator out. We're going to get started. Let's go. Okay, so this is some sort of derivative style action here. Now, even if you haven't started Unit 4, you can still solve this because it's tech active, and this is simply just typing stuff into your calculator. You should have already learned how to do this in methods. So here's my calculator, and I'm going to click Math, and I'm going to enter my derivative. So the derivative is inverse tan 2x, and then when x is equal to 3. So Shift tan 2, and then this x here, when x is equal to 3. Execute that, and we have an answer, 0.054. I can see that here our answer is 0.05. Could not be simpler. Now, I've done that on my calculator. There are other ways that can go about this, slower ways. You can find the derivative manually and then sub 3 into the derivative manually. We're not doing that. We got our calculator. Let's celebrate. Next question. So another fine example of a Unit 4 question, but you can still do it even if you haven't started Unit 4 because this is just method stuff. We're finding the area between two curves. It doesn't matter that the curves are like specialist curves. We can just type it into our calculator and our calculator will tell us the answer. Now when you start typing it into your calculator, you might panic a little bit because you can't find the sec button. But luckily you know that sec is the same as 1 on cos. So this function here we can write as y equals 1/3 times 1 on cos x on 3. Okay, what does that look like? Well, it's really like 1 on an all one fraction, 1 on 3 cos x on 3. So we just type that in. Alright, so I've also typed in my other one here, 2 cos x on 2, and I should be good to go. Now, you might be seeing this trig stuff and you might be thinking radians, degrees, etc., etc., etc. If you don't have a good reason, you should be erring on the side of radians. We're going to graph this and away we go. Draw. Okay, and you can see, looks pretty much like this. The scale might be out on the x-axis, but roughly speaking, looks the same, so I'm feeling pretty good about this. And now we've just got to find the area between the two curves. So how do we do that? On different calculators it's different, but on this one we're going to g-solve it, and we're going to go all the way over here to where we've got our integral sign, and then intersect. Click on that, and it says select lower limit value, so there's my lower limit value, so I'll execute on that. And then it says select upper limit value, I'll just arrow across. And it goes over to the next intersection point, and there we go. And we get an area, this thing here is our area, 5.706. Do I see 5.706? I don't see 5.706, but I do see 5.71, and that is my answer. Calculator skills. Celebrate, next question. Alright, we've got some complex numbers here. We've got a quadratic, and we're told that one of the roots is 2i. Okay, so if one of the roots is 2i, and p and q are real numbers, that means the conjugate root theorem's in play, so another root must be negative 2i. So we know two roots now, 2i, negative 2i. It's a quadratic, so if the roots are 2i and negative 2i, the factors of this are going to be z plus 2i, z minus 2i. So we now know, I use these little things here so that the z's don't look like 2's. I get confused all the time. Okay, z plus 2i, z minus 2i, that's going to be equal to z squared minus pz minus q. So from here, it's a simple matter of expanding these brackets and then equating coefficients. So I have z times z, which is z squared. I have z times negative 2i, which is negative 2i with a z there. I have 2i times z, which is positive 2i with a z there. That's interesting. And then I have 2i times negative 2i, which is negative 4i squared. And that's equal to all of that. Z squared minus pz minus q. Okay, what do we notice? Negative 2iz, positive 2iz, they're going to cancel each other out. I'm left with z squared, and then this negative 4 times I squared. I squared is negative 1. So negative 4 times negative 1, positive 4. And we know now that that's equal, should sort of line up my equal signs. We know now that that's equal to z squared minus pz minus q. Okay, so what does that mean? Well, we have my constant here of 4, and we have negative q is equal to 4. So if I do a little bit of working up here, I can say that negative q equals 4, therefore q is equal to negative 4. That negative is sneaky. Some people are going to think q is equal to positive 4. It's not because of this negative sitting here. What about p? Well, there is no linear term here in our quadratic. So we can just say that negative pz is equal to the invisible thing in there, 0z, which means that negative p is equal to 0, positive p is equal to 0. So, finishing things off, p is equal to 0 and q is equal to negative 4. Is that my answer? P is equal to 0, q is equal to negative 4. This is really an exercise in a couple of things: conjugate root theorem and equating coefficients. Celebrate. Alright, so we've got a big old question here, multiple parts. It's the kind of question that a teacher might give a student in a class to kind of demonstrate a property of complex numbers. But here we are, we're in an external exam, let's get started. Probably the best way to do it is to ignore everything A, B, C, D and just start with A. Okay, determine z cubed using the binomial theorem. So what's the binomial theorem? Well, it's sitting on your formula sheet. It's right down here. And it's a way to expand a set of brackets and know what all the terms are quickly instead of doing the full expansion thing. Now in this case it says figure out what z cubed is using the binomial theorem. So z cubed is equal to negative 3 plus 2i, and we're supposed to be cubing that. Okay, what does our binomial theorem say? Well, it says x plus y to the n is equal to x to the n. Okay, where's our x? This is our x. Right, and we need to raise our x to the power of n, so negative 3 cubed. Now, I know we're in specialist maths, but I feel like I really need to point out this is negative 3 in brackets cubed. The number of times I see people thinking this and getting the wrong answer. It's negative 3 in brackets cubed. Important. Now, the next part of our formula says n1. So that's 3 choose 1. You could type it into your calculator if you want, but you really should know 3 choose 1 is 3. There are 3 ways to choose one object from 3 things. 3. And then it tells us to raise x, which is negative 3, to the power of n minus 1. Now, n is 3, so n minus 1 is 2. We're doing 3 times negative 3 raised to the power of 2. And then finally, at the end, we multiply it by y. And y is this piece here, 2i. Okay, all of that is our second term. We don't have too many terms to go. This is a cubic, so we're going to have a cube term, a squared term, a linear term, and a constant term. Next term. Now, the next term is not going to be n1. The next term is going to be n2. 3 choose 2. All right, 3 choose 2. How are you going to figure that one out? I guess for the sake of zero thinking, we can go to our calculator and say, well, I want to do probability, I want to do this, and I want to do 3 choose 2, and I get an answer of 3. Sort of a balancing act, because I feel like maybe if I was doing this, I would just like scratch out the Pascal's triangle and I'd know what 3 choose 2 was that way. But, you know, it's your calculator. You're going to be really fast with your calculator, so maybe you do it that way. Who knows? Okay, so after that, we've got 3, and then what are we doing here? Well, we raised, and this is where, if you're good with the binomial theorem, you don't have to kind of follow the formula here. You just kind of start to understand what the patterns are. First, we raised x to the power of 3, then we raised x to the power of 2. Now we raise x to the power of 1. So it's going to be 3 times x to the power of 1, which is just x. And then first we didn't involve y at all. We kind of raised it to the power of 0. And then we had y here raised to the power of 1, just y. And now we're going to have y to the power of 2. So times 2i to the power of 2. And then finally, our last term here is the simplest term. We take y and we raise it to the power of n. So we take y and we raise it to the power of 3. Okay, and then we just like tidy all of this up. -3 cubed. You've got your calculator. I think a lot of people would sort of mess this up and think the answer was like -9 or something. -3 times -3 times -3 is -27. And then you've got to be a little bit careful here. 3 times, and -3 squared, that's 9. So 3 times 9 is 27. And then 27 times 2 is 54. 54i. And then what do we have here? We have 3 times -3, so that's -9. I think this is the more interesting part. 2i squared. Now 2 squared is 4, I squared is -1. So this whole bit here is -4. So we end up with -4 times -9, which is positive 36. And finally, we have this 2i cubed. Now be a little bit careful here because 2i cubed means 2 cubed times I cubed. So 2 cubed, 2 times 2 times 2 is 8. I cubed is I squared, which is -1, times I again. It's going to be -I. So we end up with -8i. Okay, that's it. Simplify this so we've got a real component and an imaginary component. -27 plus 36, that's 9. And 54i minus 8i, that's positive 48.6. 9 plus 46i. Now, I've gone through all this song and dance because I can see that the question was worth 2 marks, and they did explicitly say, determine z cubed using the binomial theorem. However, there was a lot of like maths that I had to do there. I'm a little bit concerned, but luckily it's a tech active exam. So what I would be doing is going to option complex numbers, and I'd be typing in a set of brackets here and writing something like -3 plus 2i, and then I'd be raising that to the power of 3. Yep, perfect. This is part A of a 4-part question. If I mess this up, it's very possible that B, C, and D are all going to be a mess as well. I've got my calculator. I know how to use it. I should do that. We're going to move on to part B. I'm going to get rid of all this working and just write down my answer. All right, so the next bit is convert Z, and this is Z. Convert Z into the form r cis theta, and theta is between -pi and pi. Okay, so Z is this thing here. I almost was going to use this, but no, it's not Z cubed we're converting, it's Z. All right, you can see it's worth 1 mark. So if it's worth 1 mark, I don't really have to show a lot of working. I've got a calculator. I wonder if it can help me. I feel like it probably can. Let's go options. Let's go complex numbers. Okay, and then a bit further over. And you can see we've got these buttons here. This is going to convert a complex number to polar form. This is going to convert a polar form complex number to component form. So this is the one I want. Okay, so I'm typing in -3 plus 2i. So I'm going to have to go back over here because I'm going -3 plus 2. And then we've got this I here. And then we are converting it to this. Hopefully that works. All right, I'm in business. Root 13, angle 2.55. Angle 2.55. Yeah, I'm in radians mode, so I'm going to have an angle of 2.55 radians. And that's good. That feels right because I'm between -3.14 and positive 3.14. This is positive 2.55. You might be a good idea to draw a picture and make sure that we're happy with this as an answer. -3, positive 2i. This is the complex number we're considering. So for it to have an angle of 2.55, almost pi, almost 3.14, but not quite. In the second quadrant, certainly, because it's not about less than 1.55, which is what this would be in radians. So yeah, I'm comfortable with this as an answer. Root 13, 2.55 radians. All right, simple as that. It's a complex number, root 13 cis 2.55. Next part. All right, so they really want us to do some specific kind of things in specific kind of ways. It says, use the result from question 12b. So i.e. use this result, determine z cubed using de Moivre's theorem. All right, so we're doing z cubed again, but this time we're using it in our polar form. So it's going to be root 13 cis 2.55, and that is being raised to the power of 3. All right, a root 13 to the 3, that's root 13 times root 13 times root 13, that's 13 root 13. Type it into your calculator if you want, but that's definitely what it is. And then we have cis 2.55 times 3. That's how de Moivre's theorem works. So whatever 2.55 times 3 is. 7.65. 7.65. Okay, bit of a problem because it says leave your answer in the form r cis theta, where theta is between negative pi and pi. 7.65 is not between negative pi and pi. It needs to be less than 3.14. Probably the easiest way for me to do this, because what 7.65 means as like an angle is rotating 7.65 radians around the circle. So if I just subtract multiples of pi until it makes sense, I'll be in business. So let's do 13 root 13 cis and then subtract pi from 7.65. That's 4.508, which I'm still not happy with because that's still more than pi. And if I do it again, I get 1.366, 1.367. Now, I'm very confident with that answer, but let's say I wasn't. Let's say I wanted to know whether, I've done those steps correctly. What I can do is, remember we had this polar form sitting up here, root 13, root 2.555. I can use that value right there and raise it to the power of 3. Now, some people don't know you can do this, but you can actually just kind of redo whatever happened here. So I'm going to go shift, answer, and then raise that to the power of 3. So that's going to raise this to the power of 3. All right, so you can see it's spat out 9 plus 46i, which is not that. But luckily, we already know that we can do this thing with our complex numbers, right? We can do complex, and we can take that 9 plus 46i, treat that as our answer, and then convert it. Boop. Okay, and what do we get? We get 13 root 13 cis 1.377. Okay, feels like a rounding error, but that's kind of the point of this question. So this is correct. There's a small rounding error here, but that's kind of why this question exists. All right, so I just got rid of all my working. I just kept my answer. Part D. Evaluate the reasonableness of your results from question 12A and B. 12A and C. Noting that the two methods to determine z cubed should produce the same result. Alright, so I'm just going to scribble down a little bit of stuff that I think sort of explains our thinking here. Z cubed using the binomial theorem gave us an answer of 9 plus 46i. Z cubed using de Moivre's theorem gave us 13 root 13 cis 1.367. And as noted here, these are supposed to be equal to each other. What could we do? We could convert this to this, or we could convert that to that. In either case, to compare them, we need to convert one to the other. Now, I already did that. I did that a second ago. I was talking about something else. 9 plus 46i, and then I converted that answer into polar form, and I got 13 root 13, so the magnitude was the same, but the angle wasn't 1.367, the angle was 1.377. I'm going to write that down. Okay, so 9 plus 46i when converted to polar form gives 13 root 13 cis 1.377. And now I'm supposed to evaluate the reasonableness of my result. So what can I say? I can say the magnitude is the same. I can say that the angle slightly different. And what could have caused that? Rounding errors. Right here, 2.55. that had a bunch of decimals when we did it. It wasn't just 2.55. I rounded there, and then I used that rounded figure to come up with this figure here, and that is why my angles are slightly different. So I can just say, caused by rounding errors. Now, all of this, we probably need to come to some kind of decision about the reasonableness. We should say that both methods produce approximately the same result. And we can say something like, both methods produce approximately the same result, small variation caused by rounding errors. Something like that. But the main point is that we're supposed to compare our two solutions and come to some conclusion about whether they're both about the same or not. Okay, bam. Like I said at the start of this video, this question really feels like a learning activity, like a question that your teacher would give you in the middle of class to talk about, hey, there's two ways to like raise a complex number to a power. This way is long and cumbersome. This way is super fast, and Weier's theorem is super fast. You're going to get slightly different answers, and one of the reasons for that, or the reason for that, is because you're probably going to round something at some point. All right, bam. Next question. All right, so we're going to do this question here. Now, this is the second time I'm filming this video. I filmed it once, I did my solution, but it wasn't elegant, and I want to do it again. I want to show you a better way of working through this question. So let's get started. Lots to do here. I think we really need to read the question. We need to understand it. Consider the polynomial this, and we have a cubic. But we're also told that A, B, and C in that cubic, all of those coefficients are real. And so you should see that and you should go, ooh, conjugate root theorem. There's the conjugate root theorem going on because all of our coefficients are real. Okay. Two of the roots of PZ, so two of the roots of this, are also roots of this. Okay, so that must be important information. If we want to know the roots of this, we'll probably have to find the roots of this. The remaining root of PZ is Z equals 2. So this is PZ, and it does have a root of Z equals 2. That's good information. And then we're told, given Z to the 5 minus 1 equals Z minus 1 and then this quartic, that's the same as this quartic here, determine a possible expression for PZ. All right, so, keyword, determine a possible expression for PZ. Whenever they say something like determine a possible expression, it means there's probably more than one possible expression, but we only have to find one possible expression. Okay, what am I seeing? All right, so we want to get to here eventually. We want to figure out what the expression for PZ is, and I'm seeing that I already know something about it. I know one of the roots of this is Z equals 2, so I can write something. So there's our cubic that we're trying to figure out, and we know that one of the roots is Z equals 2, which means that one of the factors is Z minus 2. And then I can write, this is a cubic, so this is going to be a quadratic, and just be careful here, PZ squared plus QZ plus plus R. Let me tidy that up. All right, so we have a quadratic sitting here, and it says that two of the roots of PZ, and the two roots are going to come from here. It says two of the roots of PZ are also roots of this quartic. So now we need to think about how we're going to find roots of this quartic. Now that quartic is sitting down here, right? And it's this crazy thing here. Z to the 5 minus 1 equals that. But that's important. Let me write that down. So this is super interesting because we're saying Z to the 5 minus 1, alarm bells should go off when you see Z to the 5 minus 1, is equal to this. Which means that the roots of this big thing here, must be equal to the roots of this thing here. So if I can figure out the roots of this, if I can solve the equation Z to the 5 minus 1 equals 0, I will have also solved this equation here and found all of its roots. We can find the roots of that. We can find them very, very easily because Z to the 5 equals 1 is a root of unity. So all we need to do is draw our nice circle with radius 1, and this is going to have 5 solutions equally spaced around that circle. So it's going to have 1 there and then 5 equally spaced. Okay, there you go, equally spaced. All right, so what are these solutions? Well, one of them is just the real number 1. This one here is also, if we're doing things in polar form, 1 cis, and then the angle, we can work in degrees, we can work in radians. Let's work in radians. There's 2 pi radians in a circle, and then we divide it by 5, so cis 2 pi on 5. Okay, this one here is going to be 2 pi on 5. 2 pi on 5 is going to be 4 pi on 5. So 1 cis 4 pi on 5. And these are conjugates of each other. These are conjugates of each other. So this is going to be cis negative 2 pi on 5. And this is going to be cis negative 4 pi on 5. All right, so we have 5 solutions, 2 complex ones, 2 complex ones. Why am I doing this? Because they're conjugates of each other, right? And that's important. Okay, let's see what we have. We've solved this equation, and we've got these 5 solutions. In solving this equation, we have also solved this equation. Now, we expect z equals 1, because that's this bracket here, which means that these other 4 solutions are also the solutions to this thing right here. Right. Good. Fantastic. Now, why is that important? Because here it says 2 of the roots of pz, there's pz, 2 of the roots of pz are also roots of this. Right? And now we know what those are. Which ones do we use? Because there's 4 roots that we potentially could put into here. This is where you get to make a choice. There are wrong answers, but there are also multiple correct answers. It says determine a possible expression. One expression could be taking these 2 roots and putting them in here. Another possible expression could be taking these 2 roots and putting them in here. You can't mix and match though. You can't grab this one and this one. You can't grab this one and this one. Why? Because of the conjugate root theorem. It's a cubic with all real coefficients. So if we've got 1 real root, 2 other roots, those 2 other roots need to be conjugates of each other. So to make things easy, I'm going to take these ones here and I'm going to put them into my equation. What do I mean by put them into my equation? Well, if these are roots of our thing, we're going to end up with z minus 2 bracket z minus 1 of the roots, cis 2 pi on 5, bracket the other root, z, and so this one is positive, so we're going z minus cis negative 2 pi on 5. Okay, pretty good, pretty good. Because now if we take this and we expand it, right, and then we can equate coefficients. Okay, so I'm going to make myself some space. I'm just going to move my equal sign all the way over to this side here. And what I'm going to do is leave this z minus 2 and then expand these brackets. So this times this is going to be z squared. So from here it gets pretty ugly, but we've got to do z times this. So it's going to be negative cis negative 2 pi on 5 times the z. And then the next term is going to be this times this. So again, it's negative cis, and this time it's the positive angle, 2 pi on 5, times z. And then it's this, negative cis 2 pi on 5 times negative cis negative 2 pi on 5. Boy. Okay, so something pretty wild happens here because we've got our cis 2 pi on 5 times cis negative 2 pi on 5. If we're multiplying our complex numbers together, we're going to multiply our moduluses together, 1 times 1, which is 1. But then we've also got our angles here, and we add those together. 2 pi on 5 plus negative 2 pi on 5, that's 0, so an angle of 0. So this ends up being 1. Okay, now you do have a calculator with you, so you can actually type in this into your calculator, and add them together, and your calculator will do the lot for you. That's fine too. Now, what about the rest of this? We've still got our z minus 2, and we've still got our z squared. But this cis thing, right, let's break it now into its real component and its imaginary component. So cos of the angle, sine of the angle, I. Alright, so that is just the expanded form of this little blue brackets in here with our z on the outside. Forgotten an I right there. That's better. And then we're going to do the same again with this piece right here. I'll have to move my 1 over. Alright, so I've just rewritten my next line, or at least started to. There's something here that maybe is not going to be immediately obvious to you. But hopefully when I explain it, we'll get there. Look what we have. We have sine negative 2 pi on 5i. And we have sine 2 pi on 5i. Okay, the magnitudes of these values are going to be the same. Right? The magnitudes of them are going to be the same. But this is sine in the 4th quadrant, which is a negative value. This is sine in the 1st quadrant, which is a positive value. These actually are going to cancel each other out because I've got sine something iz, I've got sine something iz. One of them's positive, one of them's negative. They are going to cancel each other out. Done and done. Just lightly gone. But the causes, cos negative 2 pi on 5, so that's cos in the 4th quadrant, which is a positive value. This is cos in the 1st quadrant, which is a positive value. So they are actually going to join together, join forces, and we're going to add them together. Now, it's still negative though, right? We're subtracting them both times. So negative 2 cos. And we can choose whichever one of these. Positive feels better than negative. So negative 2 cos 2 pi on 5. How am I just randomly choosing stuff? Because they're going to spit out the same value, whether it's cos 2 pi on 5 or cos negative 2 pi on 5. But it is still being multiplied by that z. And then finally I have this plus 1 on the end. Okay, that is good. That is good. Because now what I have is z minus 2. I have z squared. I have whatever this value happens to be. It's purely real. Z plus 1. So now I can expand these brackets just by doing z times all 3 of those and negative 2 times all 3 of those. Alright, we're looking good. I've just expanded the whole thing. Now I need to group like terms. So I'm still going to have a z cubed there. So that's fine. Now, negative 2 cos 2 pi on 5 z squared, and then I've got this negative 2 z squared as well. So I can group them into a single term. Let's do that. So plus negative 2 cos 2 pi on 5 minus 2, and all of that is our z squared term. And then we have a z and a z. So I'm going to add 4 cos 2 pi on 5 plus 1 z. And then my constant term is minus 2. If you're feeling a little bit lost, don't worry, because we're coming out of the wilderness right now, okay? Because we now have this incredible thing. This is pz. This is pz. Z cubed, z squared. There's my a value sitting right there. B, there's my b value right there. And c, there is my c value right there. Now, of course, you could go like one more step and like express this as a decimal value. That feels like a step backwards to me. Like you could type that into your calculator and it spits out some decimal value. But this is our exact value for whatever a happens to be. This is my exact value for what b is, and this is my exact value for c. So we can stop right there. All right, celebrate, and we are done. All right, that's it for Project 152 this week. This has been week 10. Link in the description below. Check out next week's questions. They're live now. Download them, spend the next week trying them out, and I will see you next week.